one of the basic questions in calculus, arguably the reason calculus was invented, was to figure out how the value of a function changes as the other variable changes as well. So how does the function change with respect to the other variable? Because we're talking about multivariable functions now, we can talk about how the function changes with respect to more than one variable. So that's what we want to talk about today. So we're going to talk about our first partial derivatives. First partial derivatives of z equals f of xy. So we're just going to talk about two variable function. We could extend it to more than two variables. We just apply the same argument again. So our first partial derivative with respect to z equals f of xy. So our definition. Our first, and often we just leave off the derivative. We just call it the first partial. The first partial with respect to x. And there's quite a variety of notations for this. It's written as f sub x. You'll also see with the function notation, or the variables listed, f sub x of xy. You'll also see it written as z sub x. Our new symbol, the partial derivative with respect to x. So it's a d that's kind of curvy.
Oh, that's the whole symbol?
That's our new symbol, a curvy d.
That's a curvy.
Not a delta. Delta looks like this.
God, obviously.
You'll also see df dx. So the curve on the d, it says that you're taking a partial derivative. A regular script d would be just a regular first derivative. What's that? These are all curvy, yes.
So those are actually D's?
These are all actually d's.
Like,
Just a different way to write a d. And all of these are equivalent, and this equals the limit as delta x approaches 0 of f of x plus delta x, comma y, minus f of xy. That's the change in our function value as x changes a little bit, and we're going to divide by delta x. This is the definition of the derivative, but we're letting x change, and we're keeping y is constant. So we're looking at how the function changes at a particular value of y as x changes. And yes?
So is that limit for just the top part or for the whole thing?
It's for the whole thing.
Okay.
Just like our definition of first derivative.
Plus h.
Right, x plus h. And yeah, you could write this as h approaches 0, x plus h, and h on the bottom. I wrote the delta just to emphasize that we're talking about x changing here. And with respect to y, we write this very similarly. We would say f sub y. Thank you. F sub y with our variables there. Z sub y, the partial with respect to y of f of xy. a partial of z with respect to y, partial of f with respect to y. All of these are equivalent notations, and that is going to be the limit as delta y approaches 0 of f of x y plus delta y minus f of xy divided by delta y. And we're considering x a constant. So this is saying at a particular value of x, how does the function value change as y changes? When we evaluate a first partial at a point, so everybody good with our definition? So our definition just tells us we're taking the derivative of a function just with respect to x. We treat y as a constant. Or we take the derivative of a function just with respect to y, and we treat x as a constant. All right, when we evaluate at a point, x0, y0. We write dz dx evaluated at x0, y0. And that's the same as, and this is with respect to x, we could do it with respect to y as well. We could also write it this way. And with respect to y, we'd say partial with respect to y at x0, y0. Or f sub y at x0, y0. You could also do z sub x. These are the most common ways to write it at evaluated at a point, but the other ones are acceptable. Usually, what I've usually seen is this notation more often. One of the last classes I took in my master's degree was partial differential equations. That's one of my favorite classes. So you do differential equations with partial derivatives. So you're, for example, you can talk about how heat in a 2 or 3 dimensional area changes with respect to position and with respect to time. So you just describe the temperature with respect to position and the temperature with respect to time. All right, so just to emphasize, to find f sub x, we consider y a constant. So we're just thinking about a particular value of y. And to find f sub y, we consider x a constant. So for a particular value of x, we can figure out how the function is changing with respect to y. Graphically, I'm going to draw a couple of coordinate systems, and we'll talk about what these represent in terms of our functions graphically. So there are coordinate systems. And here's a surface. And here's another surface. And I'm going to draw a curve on this surface here, like so. And I'm going to make the curve kind of thick. And what we're going to do is project this curve down here. This curve is at a particular value of y. So that line is y equals y0. So this is a curve that goes along the surface at a constant value of y. F sub x gives the slope of this curve. At a particular point. And on this other surface, I'm going to draw a curve that goes this direction. Let me make it my line a little bigger. There we go. And we're going to project that down into the plane. And this is at a particular constant value of x. The partial with respect to y gives a slope of this curve. So at a particular value of x, we can find the derivative of that curve, and we evaluate that at a point, and that's going to give us the slope of that curve at that particular point. That tells us how rapidly the function is changing as we move in the y direction for a particular constant value of x. It tells us how rapidly our function is changing as we move in the x direction for a particular value of y. And then what we're going to be interested in moving forward, one, we'll talk about our first derivatives. Today we're going to talk more about, we'll evaluate a few. We'll talk about visualizing what the first partials tell us. We're going to talk about second partials, so higher order partial derivatives. We have multiple second partials because we can take the derivative with respect to x and then with respect to y, or with respect to y and then with respect to x. And our higher order partials, we can go in different orders. We can do the x, then y, and then x again. So we get multiple different orders of higher order partial derivatives. If our function's nice things happen for our higher order partials. We'll talk about chain rules because we have a number of different chain rules depending on how x and y vary with other things. But then we're going to be interested in figuring out how our function changes in any arbitrary direction, not just in the x direction or in the y direction, in any arbitrary direction. So if we head off this direction, how rapidly is our function changing? So that's where we're going with, in part, where we're going with the partial derivatives. All right. So for these next things, I have some graphs. And we want to decide the sign of the particular partial derivatives, positive or negative. All right. So here's our surface. So it kind of goes down here, down behind, goes up here. And for part A, we want the sign is the partial derivative with respect to x at the point 4, 1. So let's go to point 4, 1, 2, 3, 4, and y equals 1. So we're kind of we're up here. So the partial derivative of x as we move in the x direction, positive x direction. Are we going uphill or downhill? Downhill. I would say it looks like we're going downhill there. Yeah, so it's the surface kind of does this and then it's doing that. So we're moving in the positive x direction. We're moving out of the screen, and it looks. I would say for A, I would say that the sign is negative. It looks like we're going downhill. How about B, the partial derivative with respect to y? As we go in the positive y direction, we're going uphill. So the partial with respect to y at that point should be positive. All right, C. -1, -2. So there's -1 and there's -2. So we're kind of at that. 2, yeah, that's -1 is here, -1 in the x direction, -2 in the y direction. So here, f sub x, as we go in the positive x direction, are we going uphill or downhill? Downhill. Going at that direction. So that would be negative. How about D? F sub y at that position. As we're moving in the positive y direction.
Positive.
I think, yeah, it's like that
It
little.
should be higher, right?
It from this contour line, it looks like we'd be going uphill. Is it a little bit ambiguous?
Yeah.
Yeah, you would need
Yeah.
to
Be straight.
You could be walking just level along that here along the side of that hill for a little bit. I'd say that one's a little bit ambiguous. Yeah.
Aren't those lines like 1, 2, 3, 4, 5 though? So shouldn't it be up like, at that first line?
So we're going in this direction.
I know,
but like
I'm saying
The
shouldn't
lines
it
on the
be,
graph
like,
are
on
That's
that
like
one.
1, 2, 3,
because
4.
that's 1.
So x is -1. Should it be up here?
Yeah.
You think? Let me see. I'm not sure that these are.
They line up on the
They
y
line up
axis.
on every other line.
So looking. I'm looking here. Maybe.
Yeah.
Maybe.
Because then we're
Then
more
it
unambiguous.
So if it lines up here,
It's definitely going up.
then we'd definitely be going uphill. Yeah. So okay. So I would say if it's there, it would be positive. If we were here, it's a little bit ambiguous. All right, so these next ones are a little trickier. The next ones in Calc 1, these are my least favorite kinds of problems. I kind of like them more in higher dimensions. It would make more sense to me.
Okay.
All right, so we're looking at a graph of a surface. We're going to have a graph of a surface, and we want to identify the graph of the partial with respect to x and the partial with respect to y. All right, so here's our surface. We have a hyperbolic paraboloid, and we want to figure out which one is the partial with respect to x and which one is the partial with respect to y. So the way I look at this one is I'm just going to pick a spot on the surface, and we're going to go, we'll look at we'll move just in the x direction. So I'm going to start here on this surface. Derivative with respect to x, when x is negative. Is it negative or positive? We're always going downhill here. Negative. And then at
X is this
0,
way.
now our derivative is 0, and then is positive, always positive. So which of these graphs, when x is negative, is always negative, and when x is positive, is always positive?
Couldn't we just identify this because y is a constant? Since it's a plane? Since y is not varying, that it has to be b.
Well, so our partial derivative is not always going to be a plane.
But then how is y a constant?
In A, x is constant.
Yeah, but that's your partial derivative with respect to y.
So-
Which way is the B plane going?
B is along the y axis. It's going like this. So B,
Because if y is a constant, it has to be a plane.
It'll always look like a sheet, right? Even if the,
no, it's not always going to be a plane.
How
I
is
mean,
it
not like a
supposed to
plane,
be?
though.
So it happens to be that way because for this particular surface, the derivative with respect to x is negative here, always, no matter where we are, and positive there, no matter where we are. So but it has to do with the orientation of the surface and the particular geometry of the surface.
Well, would there ever be a case where the geometry isn't perpendicular to the y-axis or to?
Well, let's look at the next one. Let's figure this one out.
B.
B has to be the partial with respect to x, and y, the partial with respect to y. If you move in the y direction, when y is negative, it's always positive, and when y is positive, it's always negative. And that would be A.
Thank you, Kyle.
If you cross 0, should the plane go the other way after that?
So the,
below the.
You get a little like card house after you cross 0 on graph A.
no. So this is saying that when y is negative, our derivative, this is the graph of the derivative. The derivative is always positive.
Okay.
When y is positive, we're always going downhill, so the derivative would be negative. It's below the xy plane.
Oh, does
The
does
plane goes
graph
to the
not
axis.
extend past the axis though, or the not the graph.
This?
Does it not extend past the origin?
Yes, it does. So here it's kind of going down like this. But the derivative is always negative when y is positive. We're always going downhill.
Okay.
A goes through the, like,
Yeah.
So for the slope, are you looking at the like for x, or so you said b is for x?
Mhm.
So when you're saying it's like positive and negative, is that the values of z?
No, the value of the slope.
I know. So it's the value of the slope, but how do you recognize that on the graph b?
Because, so for the x, folks, for the partial with respect to x, when x is negative, I'm always going downhill.
Yeah,
If I'm
I
go-
get that.
And then when x is positive, I'm always going uphill. So the derivative, partial derivative with respect to x here is negative, and here is positive. When x is negative, this plane is below the xy.
So that is,
that's
okay,
negative.
That z is negative.
Z is negative,
Okay,
yes.
Yeah.
Okay, I thought you meant z is negative on this.
Oh no. Yeah.
So z is negative. Z is the value of the slope.
Okay.
So z is negative here. Z is positive there.
Gotcha. So then, what does the y values don't matter then? In that?
The y value corresponds to the x and the y would correspond to x and y on the
Oh,
surface.
okay. Yeah.
All right, next one.
Oh my
Okay. Okay. We can do this, guys. Okay.
Yeah, what's that? Fake, I know. Why?
Oh, think
So let's look at the partial with respect to x. When x is negative here, is it positive or negative? As we go in the positive x direction. On this surface, are we going uphill or downhill as we move in the positive x direction?
Uphill.
Uphill. No matter where we are, we're kind of going uphill, right?
Doesn't the
So isn't the partial with respect to x always positive?
Positive?
So it's
Where is it steepest?
in the middle.
Right along the x-axis, right? Because we have that. So we're always going uphill as we move in the positive x direction. Here we're going uphill, not very steep. We're still going uphill. So the partial with respect to x is always positive. It's steepest. The slope is the steepest along the x-axis. That's going to be A. Partial with respect to y is a little different. As we move in the positive y direction, we go negative, and then we go back uphill. So as we move in the y direction, we go downhill, then we go back uphill, negative, go back up.
So Hannah, is surface B symmetrical?
Yes.
So they have,
Centimeter.
What?
they have to be along the axis that is constant.
But doesn't it depend on your x value whether what the derivative is?
Getting caught.
Like if you're
Damn.
at like x equals 4, then for the y it goes uphill then downhill. So
Yeah.
if x equals to
It
negative
goes like
4,
this.
then the y is
Line.
You're talking about this one?
Yeah.
At 4, x is positive, then negative,
It's like an extrusion of the
positive,
same
and then
thing.
negative.
Okay. But then on the other side of it, it's
Oh my God.
negative.
Negative, right?
So and
And then
negative.
positive.
Okay.
Yeah.
Just because that graph tends
Is it just because these ones are special ones? Hang on.
Mm-hmm.
So, are we like looking at a cross section kind of situation, and
No.
then like taking the cross section and extruding it? Because
No, we're plotting these graphs are a plot of z is the value of the partial derivative for a
yeah,
particular
that
value
makes,
of x and y.
that makes sense. But if we were to imagine if we were to cut that surface on the x plane.
This surface.
Yeah, that the main f surface. We were to cut it, we would then have like a little cross section that shows the values of that at a constant y. So we were to cut it parallel to the
Parallel to the
parallel to
x-axis.
the x-axis.
Yes.
And that's what we're looking at. We're looking at those parallel slices.
Not the parallel slices. We're looking at the slopes of those
Well, the
parallel
slopes of
slices.
those parallel
Yes.
slices. Well, we're
Yes.
using, so therefore the derivative has to be a single entity. Like it has to be the same for any value of the variable that's kept constant.
Yes.
Okay, so yes, it is like a cross section that you then extrude. Like you could take a cross section of anywhere on that function at a constant y, and say this is the cross section we're going to use for slope analysis.
Yeah.
And then that would be the one you'd put, and then you would just extend it to any value of y when you made your
Yes.
plot. Oh,
Yes.
okay.
Yes. Yes.
Excellent. Excellent.
All right. For this next one, we want to find
Cross sections.
the slope in the x direction
Like a couple people.
and y direction at the point. So this one, for this problem, they give us the equation of the surface, and they give us the point. So we want the slope in the x direction and the slope in the y direction. So before we actually do the work, so here's our point. Should our slope in the x direction be positive or negative? Negative. And in the y direction?
Negative.
Negative. Both of them should be negative. Well, let's find our slopes. So the partial derivative with respect to x gives us the slope in the x direction. So dh dx, we're going to take the derivative of this and treat y as a constant. So what do we get? 2x. Y is a constant. So when we take the derivative of a constant, it's just 0. So the slope is 2x. And so my notation would be d partial with respect to x at negative 2, 1, 3. We're just plugging in negative 2 here. We would get negative 4. We expected it to be negative, and there it is. Partial with respect to y.
Which number did you plug in?
I'm plugging in x equals 2 here.
Oh, okay.
Negative 2, sorry. Partial with respect to y. So we're treating x as a constant. Negative 2y. X is a constant, derivative of constant is 0. And so the partial with respect to y at negative 2, 1, 3. We're plugging in y equals 1, negative 2. So we expected both to be negative. What do you suspect is happening at this point? Slope, the partial with respect to x and y, 0 at the same time. Okay, keep that in the back of your head. All right. Let's say z is the cosine.
How many lines is this going to take?
3 or 4. We want to find dz dx and dz dy at pi over 4, pi over 3, square root of 3 over 2.
Go to 2x's.
All right, so let's take our partial derivative. The partial of z with respect to x. What do we get?
Negative sine 2x minus y times 2.
Minus sine
Yeah, so
of 2x minus y. And then we have to use our chain rule, and we have to multiply by 2. So we get minus 2 sine 2x minus y. And then we evaluate it at our point.
so you plug in both pi over 4 and pi over 3 then?
We'd plug in x equals pi over 4 and y equals pi over 3. So we get this equals minus 2 sine of 2x. We get pi over 2 minus pi over 3, which is pi over 6, which is 1/2. So we get negative 1. And the partial of z with respect to y. So we get negative sine
Positive sine delta.
of 2x minus y times negative 1.
Positive sine.
So we get positive sine of 2x minus y. So we just get, when we plug in our point, we just get the sine of pi over 6, which is 1/2. I don't have that one graphed in Mathematica. That would be a strange one. Yeah. All right, let's look at one more. Let's say that our function f of xy is 3x to the third minus 12xy plus y to the third. And we want to find where f sub x and f sub y are both 0. Simultaneously. All right, so based on what we just saw a little bit ago, what do you think is going to happen here? It's going to be flat. What happens when when derivatives are 0? Yes. I think I'm just excited when I write the y and I extend that line a little too far. So what do we think is going to happen here? No, on the surface. Our derivatives are both equal to 0. We're going to have a relative extrema. Isn't that how we find relative extrema? Set our derivatives equal to 0?
Yep.
So this kind of foreshadows what we're going to do when we talk about maximizing and minimizing multivariable functions. Our f sub x. I take the derivative with respect to x. I get 9x squared minus 12y. Y is a constant. This is a constant. F sub y is, when I take the derivative with respect to y, this is a constant. I get minus 12x plus 3y squared. And we have a system of equations. So we're going to set both equal to 0. 9x squared minus 12y equals 0. I'm going to use substitution here. So we get 3x squared equals 4y. And from this one, I get 3y squared equals 12x. So x equals y squared over 4. Now I'm going to substitute. So I'm going to substitute this in for x. So I get 3 times y to the 4th over 16 equals 4y. So 3y to the 4th equals 64y. And I'm going to factor. And this tells us that y equals 0, or y equals the cubed root of 64 over 3. So 4 over the cube root of 3. That's a 3. And this tells us from this equation that x equals 0, or x equals y squared over 4. So 1/4 of 16 over 3 to the 3 halves. No, 2/3, sorry. And I could write that as 4 over 3 to the 2/3. So our points. So this is why I said that chapter 13 gets very algebraic. This is a preview of that a little bit. So our points, where our derivatives are 0 simultaneously, are 0, 0, and 4 over 3 to the 2/3, comma, 4 over 3 to the 1/3. And we kind of guessed that those would be some kind of extreme value. Well, let's look at a picture. There's our surface. So at 0, 0, we get this point here, where the derivative with respect to x and the derivative with respect to y are both 0. And then at this point, the other point that we got, the 4 over 3 to the 2/3, 4 over 3 to the 1/3, we get this point down here.
So I mean, we just found critical points. Is there like a first derivative test where we can figure out if it's a maximum or a minimum?
We'll do a second derivative test.
There is.
Yes. It's called the second partials test. And it's a little more involved than the second derivative test. And it'll tell us if we have a maximum, a minimum, or this point is neither a maximum nor a minimum, because it's a minimum in one direction but a maximum in the other direction. We call that a saddle point.
Whoa, Sam! Whoa, Samuel!
Like sparing that.
All right. It's kind of surprising how when we start doing partial derivatives, how easy it is for students to forget how to do derivatives.
It's been a while. Maybe when you start doing derivative of the day, instead of integral of the day.
No, because then he would make it like really, really hard, like 10 different
But
changes.
derivatives are just